Okay, good day. This is Pre-Calculus. I am Mr. McCully, and this is the presentation on Lesson 45, Operations with Matrices. So let's get right to it. Today we're going to determine the dimensions of a matrix. We're going to add and subtract matrices. We're going to multiply a matrix by a scalar. We're going to multiply two matrices, and then we're going to know when two matrices cannot be multiplied, and hence we would give no solution. So we're going to do this both with and without a graphing calculator, and try and teach you how to do both of them at the same time. So first off, just kind of a review, we have touched on the matrices to solve systems of linear equations this year, but we haven't actually discussed what's going on and how to do those operations. But in general, the matrix is just a storage device. It can be manipulated in many different ways to solve problems involving many numbers. And so if you've got a big data set, you can use a matrix to manipulate it fairly quickly, and computers are actually pretty good at manipulating matrices. And the basic reason that matrices were developed was because of computing. Now I'm going to teach you how to do some of the operations by hand, and you're going to be asked to do some of the operations by hand just to get a feel for what's going on. But in general, in the quote unquote real world, you wouldn't necessarily use a matrix unless you had a calculator to do it, because the processes are a little bit cumbersome. But when you have a computer who is very good at doing cumbersome work very quickly, it becomes very advantageous. Anyway, so a matrices can be named by their dimensions, and we're going to list a matrice by its row and its columns. And so right here I have an example of a 2 by 3 matrix. It has 2 rows and it has 3 columns. And so elementary row operations for matrices, you can interchange 2 rows. So you could take 2 rows and you could switch them if you wanted to. You could multiply one of the rows by a non-zero constant. So I could just multiply this row by, let's say, 2, and it would still be okay. And then I could add a multiple of one row to another row. So if I multiply this row by 2, and then I could add them together, that is also you can do that without changing the matrix. Two matrices are said to be equal if and only if their corresponding entries are equal. So if we look at this, 2 and 3 minus 1 is 2. 3 and 2 plus 1 are equal. 4 and 2 times 2 are equal. So these two matrices are equal because what's in the corresponding cells are also equal. To add and subtract matrices, they must be of the same size, and the way we're going to do it is we're going to add corresponding cells. So if they ask you to add this is a 2 by 3 to a, let's just say as a for instance, I had this matrix went down and we had another 3, 4, and then a 1 in this matrix here. I couldn't add these two matrices because they don't have the same size. But because these two matrices have the same size, we can add the corresponding cells. So we're going to add these matrices by adding the corresponding cells. So 1 plus 2, 2 plus 4, 3 plus 6, 3 plus 6, 4 plus 1, 5 plus 3, and then 6 plus 5. And so I'm going to go 1 plus 2 is 3, 2 plus 4 is 6, 3 plus 6 is 9, 1 plus 4 is 5, 5 plus 3 is 8, and then 6 plus 5 is 11. This is our final answer. But please, what I want you to look at here is this is called the intermediate step. And so when I ask you to do them by hand, I'm going to ask you to show at least one intermediate step for full credit. The matrices button is right up here under this X inverse button, which we'll get to. And so if I wanted to do that addition with matrices, I'm going to hit the second button. I'm going to hit it to open the matrix. We have 3 tabs here. We have the names, the math, the edit column. The math column here is for a lot of stuff that they do in statistics, and we're not going to use a whole lot of it. We are going to see this determinant at some point, but mostly we're going to stay in the names and we're going to stay in the edit. Names is when we're actually doing the work. Edit is when we're putting in the data into our calculator. So I'm going to go over here to edit, and you can see that you can hold a number of different matrices. You probably won't use them all at the same time. I already have some in, and I'm going to hit 1 for A, and we need to change this to a 2x3 matrix. So here at the top we have the dimensions of the matrix, and we have a 2 for the first one. We're going to hit enter. We're going to put a 3 in for the second one, and we see that it updates it for us automatically. So 1, 2, 3, 4, 5, 6. So we'll go 1 plus 2 plus 3 plus 4, 5, and then 6 there. And when you hit enter, it moves the highlighted cell the way you would read. It moves it from left to right and then top to bottom. But if you make a mistake, you can use your D-pad here to move around the matrix if you need to make a change. All right, so once we've gotten what we want in that first one, we're going to hit second, and then we're going to hit math again. Oops, second, and then matrix. I'm going to come over here to edit. We're going to edit the second one this time, and we're going to make this one again a 2x3 matrix, and it edits it automatically. And then this one was, let's see here, 2, 4, 6, 1, 3, 5. So let's put that in there. So 2, hit enter, 4, hit enter, 6, and then it was 1, 3, 5. And remember, on that last one, make sure you hit enter and see that it has been correctly changed. So now we want to add those 2 matrices. So we're going to go quit, and then we're going to go second matrix. We're going to stay in the names column because now we're using them. So I want to hit 1 for A, for matrix A. Then I'm going to hit second. Oops, we want to add, so I'm going to hit plus. Hit second, and then hit matrix again. We're going to hit 2. We'll get their B, and then there we see the correct matrix. To multiply a matrix by a scalar, what we're going to do is we're going to multiply each scale in the matrix by a scalar. And so what we're going to end up, if you got a 2 out in front of a matrix, what you're going to go is you're going to multiply each cell in that matrix by the scalar. So it'll be 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6. And again, this is my intermediate step here. That you're going to need to do if you're doing it by hand. And final answer, 2, 4, 6, 8, 10, 12. That's my final answer. That one. All right, multiplying matrices. Matrices can only be multiplied if the inner dimensions are the same. So if you have a 2x3 matrix times a 3x4 matrix, that matrix can be multiplied because those inner dimensions are the same. But if I flip it and I wanted to multiply a 3x4 matrix times a 2x3 matrix, this matrix cannot be multiplied because those inner dimensions are not the same. The dimensions of the result matrix are the outer terms. So when I go this 2 times 3 matrix by a 3x4 matrix, what I'm looking at is the outer terms to get my resulting matrix. So again, here's another example. If I go a 1x3 matrix by a 3x4 matrix, I'm allowed to multiply these matrices because the inner, the 3 and the 3 match up. And then the result is those outer values, the 1x4 matrix. So let's talk an example here. And so we look at these examples here for these 2 matrices, and I see a 2x3 matrix and a 3x2 matrix here. And so I'm allowed to multiply these. And the resulting matrix here is going to be a 2 by 2 matrix. All right. Now, how do we go about doing it? Well, that's part of the challenge here. So the way you're going to multiply, and the reason that the rows and the columns have to match up is because that's what we're going to do. We are going to multiply the individual cells along the rows of the first matrix and the column of the second matrix. And then we're going to add those up. So in this first one, we're going to go 1 times 2 plus 2 times 3 plus 3 times -1. To get this second row first column, I'm going to take the second row and the first column. So it's going to be 4 times 2 plus 5 times 3 plus 6 times -1. To get this first row second column, I'm going to take the first row and the second column. So it's going to be 1 times -1 plus 2 times 2 plus 3 times 2. And then to get the second row second column, I'm going to multiply the second row and the second column and add those results. So 4 times -1 plus 5 times 2 and 5 times 2 plus 6 times 2. I think I made it a little big and I ran out of room, but my resulting final answer, so 2 plus 6 is 8, minus 3 is going to be 5. 8 and 15 is 23, minus 6 will be 17. -1 and 4 is 3. 3 and 6 is 9. -4 and 10 is 6. 6 and 12 is 18. All right. So as long as I didn't make any mistakes, I have it correct. So let's go and try and show that. Let's check our work with the calculator. And so my first matrix I don't have to change, but my second matrix I have to change that one. So I'm going to go over to edit, and we're going to hit 2 here, and we're going to change this to a 3 by 2, and you can see it changes it automatically, and it was 2 -1 3 2, 2 -1 3 2, and then the last 2 digits were -1 and 2. So -1 there, and then 2. And so we want to multiply, so we're going to go quit, and I'm going to go second enter to bring up this, but all I'm going to do is I'm going to change that plus to a times. Oops, plus needs to be changed to a times. Hit enter. 5 9 17 18. 5 9 17 18. We are good. So that is my correct answer. And again, there's your intermediate step. This matrix C here is a 2 by 3. This matrix C here is a, oops, that's wrong. Finally, this matrix here is a 3 by 2 matrix, and this matrix here is a 3 by 2 matrix. And since my middle two do not match up, the solution to this one is no solution. Well, that's all I got for today, folks. So the Star Wars fun fact of the day: in Star Wars Rogue One, which was in 2016, the character Grand Moff Tarkin made an appearance because it was set in a movie that was made back in 1976. Peter Cushing, the player who played Grand Moff Tarkin, the original one, which is depicted here, had actually been dead for 22 years at the time. So a man named Guy Henry played the part on set and had his face digitally altered to look like Cushing. That's all I got for today, folks. Have a good day. Bye.